Hello everyone, this is Group B5 comprising of me Muskan Bhargav and my fellow teammates Amok Joshi, Akshay Khanna and Saurabh Maurya. Under the guidance of Dr. Nadir Chania sir, we have selected computer vision based automated crowd management in bus transport service as our project topic. Before getting into the depths of our proposed project and its methodology, let us first look at what our intent actually is for taking up a project like this. Passenger overcrowding has always been a concern in public transportation, not only in India, but across the world. How many times have you been forced to travel miles and miles, standing in a bus, clutching on that handle, trying to breathe in the midst of 50 to 60 people? Plenty to make you avoid bus travel whenever you can. To alleviate the problem of congestion and to eliminate the negative impacts on the provider's transportation resources, a system that understands, detects, and exhibits crowd density is therefore required. How do we solve this issue then is the next question. Knowing the flow of passengers allows the public transportation firms to use their own resources more efficiently, enhance service quality, and decrease transportation costs. The system that we propose is thorough enough to evaluate and make observations available to commuters in advance, as well as accessible to passengers regardless of the geographical location. The system will offer live crowd density tracking and will notify both passengers at bus stop and other people about the crowd density of the desired bus, allowing them to decide whether to board the bus or wait for the next one. The system presented takes live aerial images of the crowd inside the bus using Raspberry Pi camera module. Through Arduino, the captured images are fed into the trained YOLO V5 model deployed on the Raspberry Pi that is trained to recognize the number of people and empty seats on board. For a more efficient transportation experience, the crowd count and bus location is made accessible to all the users by an Android application through the cloud server.
Now coming to the methodology of our system involves computer vision to detect the crowd density in the bus at any time. The Raspberry Pi is used as a dedicated system inside the bus in this project. After a fixed amount of time, 3 cameras installed inside the bus will continue to capture the inside view. The inside view will be the frontal aerial view. The cameras will be installed in such a way that the project will be divided, that the bus will be divided into 3 halves. These 3 portions will be processed separately and the results will be combined to produce the best outcome. The Raspberry Pi will be used to connect the 3 cameras. The collected photographs will be fed into a YOLO V5 algorithm that has been trained to detect the number of persons inside the bus at any given time. Using this approach, a pretty accurate crowd density will be generated, taking into account the current crowd as well as the bus maximum capacity. The crowd density will be utilized to notify the passengers about the bus crowding. Coming to Raspberry Pi configuration, a Raspberry Pi operating system was loaded on the laptop and etched on the SD card, which acts as a memory and operating system for Raspberry Pi. As the operating system was running, the camera port and VNC server availability was enabled. This was done by typing the sudo command in the command prompt. The camera was connected to the Raspberry Pi in the dedicated port. Now coming to the VNC server, in order to access the Raspberry Pi operating system through the laptop, VNC viewer was used. Both laptop and Raspberry Pi was made available on the wireless LAN to make the Raspberry Pi directly accessible through the laptop and remote. A new user was created using a sudo command, sudo add user command. To access the camera, required Python libraries and OpenCV libraries were installed. To access the live stream of the camera, OpenCV packages were run on Python environment, which is Thorny. The live stream was made available on the internet and was accessible using the IP address. As you can see, this is a basic RPi and RPi camera installation setup. And as we can see in the picture, the camera quality of the cameras that we are using is pretty accurate, and we'll be learning more about the camera quality in the data creation part.
So speaking about the dataset creation part, we actually created a novel dataset of our own by capturing the real-time area view images inside the public buses. So the main motive behind doing that was to introduce an element of novelty and to do something which hasn't been done before. So as we can see, 3 cameras were interfaced with Raspberry Pi and were fixed inside the buses, and 3 aerial views were captured, that is left, mid, and right respectively. But after that, one major concern was the overlapping views of all these 3 aerial images. That we can see that there are some portion of seats which are present in all the images. So to overcome this issue, what we did was something called as ROI cropping, which is seen in the next slide. So let's take the left view for instance. So the leftmost image is the original image, and the middle image is the region of interest cropped image. So what basically ROI cropping does is basically it takes 4 coordinates of the polygon as input, which we provided by some trial and error testing, and finally fixed up the 4 coordinates. And those 4 coordinates were the same for all the images which belong to the left view. So what this did exactly it did was that it basically confined the view of the for our model to a particular fixed area, and that is it neglected all the other remaining areas of the image. And the rightmost image is the final image, which shows that all the people present in the view concerned are detected successfully. Similar approach was done for the mid view and the right view as well. Speaking about the results, before that, I would like to talk a bit about the YOLO VIFA architecture. So YOLO VIFA is a convolutional neural network which is used for object detection, and this is what we have used in our project as well for the crowd detection part. So speaking about it, as we can see, the architecture of YOLO VIFA consists of 3 major parts. That is the backbone, the PA net, and the output layer. So the backbone basically is the CSP darknet, which is another model. So the role of backbone is basically feature extraction. So the first initial feature extraction happens in the backbone, that is the CSP darknet. Second is the neck, that is the PA net. The neck is basically used for image scaling and detection of the objects. After that, we come to the head, that is the final layer, which is also called as a YOLO layer. YOLO stands for you only look once. So the data are first input to the CSP darknet for feature extraction, which is then passed to the PA net for feature fusion. Finally, the YOLO layer outputs the detection result, that is the class, score, location, and the size. Moving ahead with the results, as we can see, the results in all the 3 aerial views, that is the left view, mid view, and the right view, are successfully locating each and every person in the image. Specifically talking about some harsh cases, that is in the mid view, we have kept an image in which the person standing at the last is pretty hard to detect for the model, but still our trained model successfully detects it, giving a high accurate of crowd density. Now I would like to talk about the statistical analysis of the results. So we have used TensorFlow as the machine learning library for our experiments. So along with TensorFlow, there is another library attached to it called as TensorBoard, which helps you analyze the model's performance. Using TensorBoard, we got an accuracy of 99.54%, and also the results were plotted using matplotlib charts. So the results are shown in the next slide. As we can see that there are 2 major losses associated with object detection problems, that is the bounding box loss and the object loss. Both are plotted for the training set and the validation set as well. Also, some accuracy metrics like precision recall are also plotted, thus giving a fairly enough idea of the statistical analysis and how well the model has been performed. We also saw the quantitative analysis as well, that is all the people in the frame were accurately being detected. Moving ahead with the next slide. Okay.
Moving to the GPS part of the project. So GPS system has been installed with the Raspberry Pi system in the bus, and as the bus moves between the stations, it locates and gives the coordinates to the crowd server. So how it has been done, we will see here. So GPS has been interfaced with the Arduino to give the basic coordinates, as you can see here. So after getting interface with the Arduino, we can get the coordinates of the current location where the GPS system has been installed. And while we install this whole system in the bus to get the location of the bus, and we can send this data via Firebase to the application. So now coming to the user interface of the proposed application, we have created a real-time database for our application, where this real-time database is supported by an admin login, where this admin has to get all the data from the bus, that is number of crowd count, seat availability, and the location from the bus, and it saves it into the real-time database storage. As we can see here, a route from Kurla to Chembur has been selected. That's number of bus traveling between these routes and the crowd density of those buses. So this data is when now then projected to the application's final page where user can see and choose which bus to board. As we can see here, this is a sign-in page where user can log in and move ahead to search from where and to where to go. So here she can see the number of bus that is available in Kurla to Chembur route, that number of the bus, and this is the basic overview, that is seats availability, crowd density, and the route has been displayed by the unique ID called bus number. Now coming to the conclusion of the project, the system will prove to be the great help in solving the problem of overcrowding in the public bus transport. Using the YOLO V5 model will provide us with faster computing and prove to be efficient for crowd detection, which has been done here. The Android application service will make it possible to provide information to commuters at the bus stop and also to the prospective commuters away from it. Thus, the proposed system proves to be an effective solution to manage the overcrowding problem in the bus transport. Thank you.